Alright, let's solve this problem carefully from the beginning, because there is a nice little geometric idea hidden inside it, and once we identify that idea, the algebra becomes much easier. We have a square with a side length of 14 units, and inside this square we have an irregular hexagon. Now, even though the hexagon is irregular, we are told something very important. All 6 sides of the hexagon have exactly the same length. Let's call that common side length, y. Our job is to find the value of y. So, first, let's focus on the small right triangle in the lower left corner of the square. This is where the main idea comes from. Remember, the entire side of the square is 14 units long. Along the bottom of the square, the hexagon occupies a segment whose length is y. So the part that is left over, which forms one leg of our little right triangle, must be the entire side of the square minus that y. In other words, this horizontal length is 14 minus y. Let's write that down, 14 minus y. Now notice that exactly the same reasoning works for the vertical side of this little right triangle. The entire vertical side of the square is 14 units, and the hexagon takes up a length of y along that side. So, the remaining vertical distance is also 14 minus y. This is an important observation because it tells us that the 2 legs of our right triangle have exactly the same length. Both legs are 14 minus y. And what about the diagonal side? Well, look carefully at that diagonal. It is actually one of the sides of our hexagon. Since every side of the hexagon has length y, this diagonal has length y. So now our right triangle has 2 legs, each measuring 14 minus y, and a hypotenuse measuring y. This is exactly the situation where the Pythagorean theorem can help us. Remember, for a right triangle, the Pythagorean theorem says that the square of one leg plus the square of the other leg equals the square of the hypotenuse. So, we can write 14 minus y whole squared plus 14 minus y whole squared equals y squared. If you're following along, this is a good point to pause and try the next step yourself. And if you enjoy these geometry problems, don't forget to like the video and subscribe for more. Now, notice that the 2 terms on the left are identical. We have the same quantity, 14 minus y whole squared, appearing twice. So instead of writing it twice, we can simply multiply it by 2. Therefore, we get 2 multiplied by 14 minus y whole squared equals y squared. Now we need to expand the squared expression. Let's be careful here. 14 minus y whole squared means that we multiply 14 minus y by 14 minus y. When we expand it, 14 multiplied by 14 gives 196. Then 14 multiplied by negative y gives negative 14y. Next, negative y multiplied by 14 gives another negative 14y. And finally, negative y multiplied by negative y gives positive y squared. Combining the 2 middle terms, negative 14y and negative 14y gives negative 28y. So 14 minus y whole squared becomes 196 minus 28y plus y squared. Therefore, our equation becomes 2 multiplied by the quantity, 196 minus 28y plus y squared equals y squared. Now distribute the 2 across every term inside the parentheses. 2 multiplied by 196 gives 392. 2 multiplied by negative 28y gives negative 56y. And 2 multiplied by y squared gives 2y squared. So now we have 392 minus 56y plus 2y squared equals y squared. At this point, we want to collect everything on one side so that we have a standard quadratic equation. We can subtract y squared from both sides. The y squared on the right cancels with the y squared we subtract, while 2y squared minus 1y squared leaves us with 1y squared. So the equation becomes y squared minus 56 y plus 392 equals 0. Great. Now we have a quadratic equation, and we can solve it using the quadratic formula. Remember, the quadratic formula says that y equals negative b plus or minus the square root of b squared minus 4 ac, all divided by 2a. Now, let's identify a, b, and c from our equation. Our equation is y squared minus 56 y plus 392 equals 0. The coefficient of y squared is 1, so a equals 1. The coefficient of y is negative 56, so b equals negative 56. And the constant term is 392, so c equals 392. Now we substitute these values directly into the quadratic formula. Since b is negative 56, negative b becomes positive 56. So we get y equals 56 plus or minus the square root of negative 56 whole squared minus 4, multiplied by 1 multiplied by 392, all divided by 2 multiplied by 1. Let's calculate this carefully rather than rushing. First, negative 56 squared is 3,136. Next, 4 multiplied by 1 multiplied by 392 gives 1,568. Therefore, inside the square root, we have 3,136 minus 1,568. Subtracting those gives 1,568. So, our expression becomes y equals 56 plus or minus the square root of 1,568 divided by 2. Now, we need to simplify that square root. Notice that 1,568 can be written as 784 multiplied by 2. And 784 is 28 squared. So 1,568 is 28 squared multiplied by 2. Therefore, the square root of 1,568 becomes 28, multiplied by the square root of 2. So now our two possible answers are y equals 56 plus 28 multiplied by the square root of 2, divided by 2, or y equals 56 minus 28 multiplied by the square root of 2, divided by 2. We can simplify each one by dividing every term in the numerator by 2. That gives us two possible values, y equals 28 plus 14 multiplied by the square root of 2, or y equals 28 minus 14 multiplied by the square root of 2. Now, this is where we have to be careful. Just because the quadratic formula gives us two mathematical solutions does not mean both solutions make sense for the geometry. We have to check which one actually fits inside our original square. Remember, the side length of the entire square is only 14 units. Therefore, the side length y of the hexagon has to be smaller than 14. Let's check the first solution, 28 plus 14 multiplied by the square root of 2. The square root of 2 is positive, so 14 multiplied by the square root of 2 is also positive. That means 28 plus 14 multiplied by the square root of 2 is definitely greater than 28, and therefore, it is certainly greater than 14. So that value cannot possibly fit inside our 14-unit square. We reject that solution. That leaves the second solution, y equals 28 minus 14 multiplied by the square root of 2. This value is less than 14, so it is geometrically possible. We can also factor 14 from the expression. Taking 14 common gives y equals 14 multiplied by the quantity, 2 minus the square root of 2. If we want a decimal approximation, the square root of 2 is approximately 1.414. So 2 minus the square root of 2 is approximately 0.586, and multiplying by 14 gives approximately 8.20 units. Therefore, the length of every side of the hexagon is 28 minus 14 multiplied by the square root of 2 units, which is approximately 8.20 units. So the key idea was to isolate that corner right triangle, recognize that both of its legs are 14 minus y, recognize that its hypotenuse is y, and then use the Pythagorean theorem to turn the geometry into a quadratic equation. If you got the same answer, definitely let me know in the comments how you approached it. And if you want more problems like this, make sure to like the video and subscribe.